Okay, so thanks everybody. I would like to be with you, but unfortunately I only can join online. So here is my online presentation. As you will see in 2-3 minutes, it's slightly experimental, so let's hope it works. Now, the talk is about granular matter upscaling, and I will show you some steady state results, some more new elastoplastic results on granular matter, also on transitions, and I will go to mesostochastic events, and I will explain you what I mean with that. Before I do this, I want to say some words about keywords or nomenclature, and also to avoid confusion with the previous talk. Okay, maybe not confusion. The previous speaker was evidently talking about things like aging or memory and so on. I also will talk about similar things, but sometimes I will use different words. So I want to just quickly throw some words at you, such that you are not too shocked when I say something which is not exactly in the same language as the previous speaker. So sorry for, I will create confusion probably. Now, in rheology, you have words like viscoelastic, elastoplastic, thermoviscous, mobility, aging dynamics, relaxation times, and you think of polymer melts, for example, and many other materials. Now, I will use mostly words like solid-like and fluid-like because that's in the granular community used, but that is related to the keywords from rheology. Sometimes I will say something about elastoplastic, plus viscous, plus thermal things in theory or numerical context. I will talk about transient dynamics, or at least I will try to get there. Okay, so, and there are other keywords which I will use. Stochastic, I will have to explain what I mean with that. Thermodynamics, I'm not claiming that I do non-equilibrium thermodynamics, but the systems I'm talking about are not in equilibrium typically. And upscaling is also related to nanoparticles, microparticles, mesoparticles, but the context will become more clear. I will not only refer to particles, I will refer to different scales of observation. Okay, and I will in some part of my talk about work, heat, entropy, which are very classical concepts. And as I mentioned already, solid-like, fluid-like. I want to go beyond the classical concepts, and granular materials, in my opinion, are already beyond, so we only have to understand them, and then we are beyond, whatever that means. And something like a granular thermodynamics with a question mark, so you will see. Now, the overview of my talk, I have two parts. The first part actually is recorded, and I do this for the first time. So I don't know if you want to stop me and ask questions during the recording. I'm not sure whether that will work. So maybe you keep your questions for later, because in the second half hour, I am surely happy to take any questions. And also interactively, I want to focus on one or two of the items which are mentioned in the first recorded part. So the experimental thing is the recording, which should start now, and then for 28 minutes or so, I will not talk interactively, but I'm ready to take urgent questions if there are. Otherwise, please wait a little bit longer, and I'm surely happy to take questions later. So let's hope the recording starts now and is working. If not, I will just continue without recording, but the recording should start now. Thank you for the invitation. And unfortunately, I cannot attend physically. I miss you all very much, but I hope you can at least see my recording of my plenary talk. The talk is about steady-state flow rheology. That's the first part, and elastoplastic transitions and mesostochastic events. That is the more recent results which we have got in the last few years. So the question is, why are granular materials interesting? Now, from the natural science point of view, physics related, they are interesting because they can exhibit liquid phase, gas-like phases, like in a sandstorm, and solid phases, like on the beach when you can walk on them.
Now, how do we approach the system? How do we do the micro-macro transition? So first, we take a look at particles. And for the particles, we have to define the contact model. Then the discrete particle model or the discrete element simulation contains the contact information, the particle information. Then you can simulate many particles, for example, like here, flowing down a tube, flowing down on a slide. Okay. And on the bulk scale, the real macroscopic world, that is the world of continuum models. How can we go from a particle, many particle model to a continuum model? And if we have this, then we can solve real avalanche problems, for example, on the macro, on the continuum scale, starting from the smaller many particle system and starting from the microscopic or nanoscopic contact models. If we have a micro-macro transition like this, we can change the contact model and can see how that changes the macroscopic scale. So how to do this? How to approach this? First, let's take a look at the microscale and translate information from the local particles to the continuum scale, to the macro scale. The first example I show you is a silo flow, and here you see particles, they are flowing down. Here's the outlet, and we can evaluate the system information at different points, or we just can view the fields in the whole system. Now, for fields like density, this is how density looks like. The density is lower in the shear bands and at the outlet. This is momentum density, momentum or velocity. The velocity is highest close to the outlet, and it gets down to very small values in the stagnant zones. Okay, and then we have strain, which is non-symmetric. The different colors left and right tell you it's non-symmetric. Now, for the rest of the talk, I have two parts. First one is steady-state rheology, and the second one is about fluctuations, elastic plasticity, and mesoscale events, which I will explain later. Now, after we have done this, next thing is to deduce non-Newtonian rheology, constitutive relations. Now, more general, the mu of I rheology represents the orange line. That is the critical state, the steady state flow when a fluid remains a fluid because it's driven and sheared all the time. Now, but there are also other things which are interesting. When you start from a stagnant solid-like state and you start shearing, then you will reach a yield locus and the solid will become fluid. Or when you are in the fluid critical state and you stop and relax, then the fluid will become a solid. So these transitions are also very important subjects of our research. In the steady state, which is the main focus today, we know now how to translate information from local particles to continuum and how to deduce some type of materials rheology. But what if we have dry materials? What if we have frictional materials? What with different friction coefficients? What if we have cohesive materials or wet? Now, how to do that? So worked on this, and a simulation, a cut, a zoom into the system allows me to display what we are doing. So blue are particles at rest, red are particles which are moving with the outer wall, and green is where the shear band is. The array here tells us where do we evaluate the data, and this gives us a set of shear rates, shear stress, normal stress, density, and others. Information on every point of the system, on every of these grid areas. Okay. And with this, we can plot constitutive relations. So, for example, shear stress against pressure. All the data with a moderate shear rate or larger collapse on this friction law, on this Coulomb-like constitutive relation, which is the straight line. Okay, and the slope, that is the macroscopic friction. However, when we plot shear stress against normal stress, here we do it with units, then we see that increasing friction particle contact friction coefficients give us an increasing slope of this friction law, this mu of I law. Okay, and this is the slopes plotted against the particle friction coefficient. So it's increasing and then it's saturating. Okay, this is what we can get easily out of it. Now, given a set of simulations of different materials, which material parameters match with the experiment? Okay, so here you see experimental data of shear stress versus normal stress, different materials, different particle sizes, in this case, different coercivity, and actually also different devices, FT4 and ring share testing. Now, given the experimental data, we can match the simulation parameters to match the experimental data. That is called calibration. Or, given a set of numerical material, we can find experiments which validate the simulation. So we can do both. Okay, now, for rigid particles, there's an effect of strain rate. And I is the non-dimensional strain rate. I come back to that one. And the bulk friction follows the mu of I rheology for many different simulations. Different colors are different simulations with different situation, different global shear rates. The coordination number, the particle contact number, is also following a trend, but it's more complicated. There's this zigzag structure here, but they follow a trend also. I will not talk about coordination number today in detail. Now, for the macro friction, the solid line is well fitted up to a certain extent by a linear function in I, where alpha is almost 1. Okay, so constant plus a linear function in I. Note the logarithmic axis here. Now, what happens if I do not only change the shear rate, but I also change the stiffness or gravity? It gives me no data collapse to begin with, but if I find a right dimensionless combination, then the data actually do collapse. I can also rewrite this a bit, express it as dimensionless stress, and then the collapse data for many different simulations follow also a trend, and the friction is actually going down. The bulk friction is going down with the non-dimensional stress. They are collapsing, but the trend is qualitatively different. And this looks like constant minus function of pressure, dimensionless pressure, to the power beta. And here beta is 0.5. So in my definition is we take the additive thing, but we replace it by a multiplicative thing because that's much more handy. And the additive terms come out from the multiplication, but there's also a nonlinear term popping up, which actually it's hard to quantitatively deduce from particle simulations, but actually it might be there. And then the multiplicative rheology has the advantage that it's directly involved. Okay, now anyway, each of these linear terms is linear, yes. Each of these first order terms here is linear, actually linear in time scales, not in pressure. Okay, and the nonlinear term definitely is not linear, but we have a first order linear model this way. We did this in 2015 and later in 2017. What if we have cohesive particles? We have another correction, which we constant, add to the constant as a linear and actually a quadratic term in the bond number. And all these terms are, almost all of them, except the bond number term, all of them are linear to first order. Now, as a summary of my presentation, I talked about steady state flow rheology. We have a micro-macro based constitutive model based on inhomogeneous DEM simulation. And we could present a rheology which is quite general in quite some material properties. Micro-macro allows us to predict the macro flow behavior, and this can be used in continuum solvers. And the corrections are all formulated in dimensionless numbers, ratios of timescales here. And in general, all of them are needed, and all of them appear linear to first order. Thank you.
Oh, for the second part of the talk, it's more about unsteady state. It's about fluctuations, unsteady state. It's about transients. It's about rate dependence, and it's about mesostochastic events. Some of these things I will address in the second part of my talk. Some of them are too much. Consider shear stress versus shear strain. So the difference between shear stress, epsilon is shear strain. And the blue line is shear from isotropic state during a certain time with a relatively slow rate. Now, what happens during shear is that you have elastic regimes and you have plastic events. So there's a mix between elasticity and plasticity. In this resolution, you cannot see it. I will zoom in later. Okay, but in this stress strain picture, we can analyze a little bit of fluctuations. Okay, how do we do this? So we take the probability for stress going up, we take the probability for stress going down, that's on the horizontal axis here. Delta sigma being positive or negative means your stress will increasing or decreasing. And the delta epsilon is the range which we look forward. Okay, so if we use a small range, we get a narrow Gaussian distribution, it's almost random. If we use a wider range, then we get something which is not Gaussian anymore, it's actually two-peaked, and it's not non-symmetric left and right. Okay, so that's for larger delta epsilon than now, if you do the statistics a little bit more detailed and so on, and better statistics, then you get the probability and you see the yellow distribution. It's not centered around zero, it's slightly positive, that's the elastic regime, and it's plastic on the negative side, and it's highly asymmetric. So the probability for elastic events is exponentially decreasing, so that's normal statistics. On the left-hand side, you have the possibility for rare events. So the low probability for big stress drops. Okay, and that is special. So keep this picture in memory, we come back to it. The two plots, one plot is hidden by my face. The two plots are just different densities. It's qualitatively the same. The details at low density, high density are different. Okay, but what is important is we have the probability for elastic events, stress increase, delta shear stress. Shear stress changes with proportion to shear strength. On the right-hand side, negative are stress drops, and what those are, we'll explain later. Okay, so this is the statistics about the fluctuations. Parallels continuum. I did not yet bring in the rate dependence, and I introduced the probability for events, so elastic behavior and plastic stress drop events. So what is going on? The evolution of stress, the fluctuations which you saw, the statistics. Under any type of deformation, I only showed you shear so far. Under any type of deformations, there are two possibilities, elastic, and that's what I call reversible events, elastic stress changes. They will be reversible by definition, and plastic, and they will be irreversible. In order to understand what is going on in a stress-strain situation, left plot, this stress-strain, as we saw it before, we want to analyze it. So we have a MATLAB script which is taking all the stress drops and numbering them, and then we can do statistics based on the stress drops. So in the left plot, you see stress-strain, as we had before. In the right plot, you see delta stress over delta strain, which gives us the elastic shear modulus. That's the horizontal level here. It gives us the stress drops which are going negatives, and it gives us a few rare events which are going slightly positive, at least for a short time. So that are stress jumps, but they are very rare. Stress drops are the normal thing which are happening, and they are happening at different magnitudes at this point. Now, when you do the analysis, you get a lot of data, a lot of statistics, and then you want to clean up and plot a histogram which involves the jumps, the drops, and the big drops. And we want to understand whether the small drops are really relevant, whether the big drops are more relevant. The big drops are the interesting ones, by the way. A lot is going on. Okay, and then we can do statistics, and we get something like average change in stress, average change in modulus, and some other things, as you will see on the next slide. This is now the zoom into one event. We are looking at stress, we are looking at modulus, we are looking at kinetic energy, and we are looking at coordination number. At the top left, you see the shear stress. That's the orange line, and there's the stress drop, shear stress drop. The blue line is the hydrostatic stress. Actually, there's a little bit going on, but not much. Only a wiggle, no drop. Okay, so hydrostatic stress and shear stress are qualitatively behaving differently for this event. This is the modulus, delta stress over delta epsilon. And the modulus doesn't change too much. There's a drop. The modulus is not active. The material has no elastic stiffness during the event. And then it goes back to almost the same level. Kinetic energy is bottom left. So here, at the event, at that what we identify as the event, kinetic energy is going up, and then it's shooting up after the event even much more, and then it's exponentially decaying. So this is one of the event, kinetic energy going up by orders of magnitude and then going down again. And the plateau, this is the elastic area, and the event where the particles are moving around and rearranging, this is that what I referred to as plastic, as irreversible before. So you can go from here before the event to another point before the event and back, that's reversible. When you go from before the event to after the event, you cannot go back. This is irreversible. Okay, and finally, we look at the coordination number sometimes. Here, not much is happening, but there are much more violent events where the microstructure, the contact network is changing number a lot. So in summary, what we learned from our particle simulations, and I didn't make that clear yet, only if we really go slow, very, very slow, then we can identify these isolated events. Isolated events are plastic, irreversible, and they interrupt the reversible elastic base state. Okay, and for this one, you really have to go slow enough. Most of the time in finite size systems, experiments, you have too many particles and you cannot go that slow. In simulations with small system size, a few thousand particles, 10,000, 20,000 particles, we can go slow enough. We have to be patient, but then we can distinguish the stochastic plastic events which interrupt the reversible elastic state. Now, there is a special case, and that is when you have an unjammed system and you shear and the system jams, as was presented by particle simulations by Vescovi et al. A few years ago. And we made the theory for this, which gives density and coordination number and pressure, all the continuum quantities. And the red arrow indicates the jamming event. So there is a possibility that you have an unjammed system, you shear and you jam the system. In simulations, it's the green line. In theory, it's the blue line with the marker. Now, this is the animation of such a shear event. It's a special situation. You go from unjammed to jammed in a volume-conserving shear system. And actually, you can go cyclic shearing. You can go shear forward, backward, but I won't show too much of this. Okay, now the question is, how much do you have to strain in order to have the system sheared? And the second question is, what is going inside the force network of the system during shear jamming, during this shear jamming? So first the system is unjammed, then it's becoming fragile, and then suddenly it shear jams. So the details about this slow enough, 10 times, 100 times, 1,000 times slower than you are normally used to, those are published in Pulses and Grains 2021 and will be published shortly in Frontiers 2023, also including system size dependence study. So I don't have the time to go into details here. I'd rather continue with something else interesting. Now, in order to formulate this theory, which I mentioned, which I showed you some preliminary results already, we have to appreciate one more thing, and that is the jamming diagram, but in event-related form. Note that many interesting things are happening. So we have history dependence, we have slow relaxation, we have creep, aging, we have shear jamming, as I showed. And we have the jamming point, which is not a point, it's a variable. This has to be appreciated
And only if this is appreciated, then we can formulate this general theory, which includes the events, their probabilities for events, and which includes jamming, unjamming, fluid-solid transition, gas states, fluid states, and solid states, as it's so interesting for granular physics. Now let's take a look at stress versus density. We come from unjammed, low density, we compress up to a certain magnitude of density or stress, and then we go back. So the green line is going up to density 0.68, volume fraction 0.68, and going back. And this already shows that the jamming density at the beginning, at the loading, is not the same as the unjamming density at unloading. The red is going up to a much higher density and coming back. The red dots, big dots, are the back branch. The small dots are the loading branch. Big dots are unloading. Okay, the amplitude of the difference increases. The blue lines are the 100th time of loading and unloading, and actually it becomes close to reversible. It's not exactly reversible, but it's getting close. And it's different again. So the blue line is the same system as the red system, same system loading parameters, but after 100 times, it has a different jamming density. So it's much different. Jamming density is not a constant. It's not a point, it's a variable, and that has to be taken care of. Now, left you see pressure, some of the data. The points are particle simulations, the lines are the continuum theory from 2016, actually. We had a quasi-static continuum theory at that time, which worked pretty well. And the right data are experimental data, soft hydrogel particles, which confirm the loading and unloading jamming density is not the same. When we plot kinetic energy for those two cases, we see something similar as we saw under shear. There's an elastic baseline, the lower envelope of the data. There are peaks, events, which are happening under isotropic compression. So what I showed you before for shear also happens for isotropic compression, for loading and unloading with different probabilities, but that's something for further analysis.
Coordination number.
And then we apply the same event analysis as we did for shear. For loading, we have a lot of stress drops, as you see on the left figure. And for unloading, we have actually stress rises because we go the other direction. And the green dots in both plots are also showing the asymmetry of the probability distributions. Take the statistics and calculate the probability for isotropic events instead of shear events. We are talking now about isotropic compression. That is a different type of event than for shear events, but the statistics, the non-symmetry, the non-Gaussianness is very similar in shear and isotropic. Okay, also when you clean up the data, remove the messy part with the small events, we get the probabilities, and those we can bring into the continuum theory. And with this, the continuum theory is finished. Only the shear is not sufficient. We also need the isotropic events. Okay, and then we do the same as we did before for shear. We zoom into one event. Stress drop or stress fluctuations are happening close to jamming. Violent wiggles are happening. At high densities, the situation is slightly different. But some features like the stress drop and the kinetic energy rise and the change in modulus and the change in coordination number, they can be much bigger because the confining stress is higher, so the events can be much more violent. So this is one example. And also you see the event very isolated because for high densities, for high confining stress, the events are more isolated than for low confining stress close to pressure. Okay, and all this is taken care of by the probability for isotropic plastic events. Now, this is the summary of my presentation.
My presentation was about fluctuations in steady state, and we were looking closer and closer and closer. We did particle simulations and we translated things to continuum, and we deduced observed mesoscale stochastic events. Those we explain by the stochastic event probability for isotropic events, for compression, decompression, and for the shear isotropic events. I started with shear, I showed you compression later. Now, the universal continuum theory we published 2 years ago in Granular Matter, and you can read the details there. The essential pieces in the continuum theory are these two probabilities, PV and PS. So, and I showed you the microscopic origin, the mesoscale origin, the restructuring of the contact force network, which goes into the continuum theory. We also did stochastic modelings. We actually did that already a few years before, and that's based on a master equation taking into account the probability densities, the transition probabilities from one state to the other. So that's a back reference. Thank you.
So this was the recorded part of my talk, and I'm happy to take questions now anyway, and then I can switch to the second part of my talk, which is interactive. Okay, are there questions now? Because I will go into details concerning 2 of the items, so you also can wait for those, or I will refer you to the second part of my talk. Are there any questions now?
I don't see, so you can probably go to the second part, please.
Okay, thank you. And sorry, 1 or 2 of the slides had really bad sound level. I hope you could hear it anyway. I hope you could hear it throughout. So I switch now to the second part about granular matter rheology, fluid and solid like behavior state transitions, and so on. The keywords I mentioned already, so I skip over those. I want to advertise work which is related in spirit, but which was done by polymers or polymer melts. So you know the rheology G prime, G double prime for polymer melts where you have colloidal particles in. In this type of models, my colleagues, it was not my own work, it was by my colleague Lothar den Otter and Wim Briels, they have developed a numerical model for simulating polymeric melts with colloidals, and they observed shear alignment, shear migration, and such things. And from these models, they also could deduce different types of model: polymer solution, polymer melt, warm like micellar solutions, and they could deduce the G prime, G double prime as function of the agitation frequency. Okay, so this type is a micro-meso macro model in some sense. It's called RAPID if you are interested, and its application to polymeric systems plus particles in it, but the polymers play the big role here. Okay, so just an advertisement. The other keywords, you heard some of them through my talk, and some of them need a little bit more explanation. The states, what I refer to as state, is the state of solid, state of liquid, state of gas. And state transitions are transferring from solid to liquid, liquid to gas. I will not talk much about gas. It's mostly about solid to liquid or liquid to solid. Okay, now, one thing before I go to the details is that you always need some experiments in order to classify the system, in order to measure what is going on in the real system, not in the numerical system. I didn't talk much about experiments, but I want to refer to. Okay, now, there are state variables in a theory, and there are also state variables which are relevant for your material. And the state variables, I can plot 2 state variables in a 2-dimensional diagram. One is the confining stress, horizontal right, and the other one would be the shear rate, vertical down. Okay, and the green abbreviations and the yellow abbreviations are experimental devices which work in certain range. So GranuHeap and GranuDrum work for not too high confining stress, for low and high shear rates. a tabletting simulator will work at extremely high confining stress and very high shear rates. And the classical shear testers work on this axis, tensile or compressive sheared. Okay, so these are experimental devices, and with these devices you can measure different things. In geotechnics, you are typically interested in higher confining stress. In process engineering, you are interested in lower confining stress. In tableting, you are interested in very high confining stress and very high rates. And there are other processes to think about. Okay, so this is a reference to experiments. And unfortunately, there are many, many different experiments, and not everything. No, sorry. I claim you cannot get all the information which you want from a single experiment, because that one is only working in a certain range and not outside. Okay, so keep that in mind. One example of our work where we did some experiments was the tensile powder testing. And we were bringing actually the new experimental results and old experimental results together. The gray surface is a classical thing from 70 years ago, so-called the Wroclaw surface, and it brings all the experimental data on this surface in the shear stress, void fraction or volume or density on one axis, on the other, sorry, shear stress on the vertical axis, density on another axis, you can call it different names, and normal confining stress on the axis to the right. And all the experimental data are fitted by this nonlinear surface, and the blue line and the red line are special cases. The red line is related to the yielding from the previous speaker, but it's also related to the initial consolidation in the soil mechanics community, or to the jamming density, as I mentioned in my previous talk. So here, with this plot, the different communities come together, but still the different communities are using different languages. I was using my language. Sorry if that sometimes was not the wording which you are used to. Okay, and this is experimental data where we brought different elements together into one theoretical best fit to the experimental data. And then if you have a best fit, you also can work with theory or compare to simulations. Okay, so that was one thing. Another thing which I will not talk about much, unless you ask me, is powders. This is a numerical model with our open source package Mercury DPM. Powders, relaxation, compaction by stress, and then sintering, where you increase the temperature, decrease the temperature, and this way increase the packing density. Okay, so we are also working on this, but I don't want to go into those details unless you ask me. Good, now I come back to the conclusion of the recorded part, and I have two details prepared. Okay, so elastic plastic, relaxation creep, granular temperature, I didn't talk much about, transients and state transitions. I showed you one or two examples only, but I didn't show you the theory which we developed for this. The other thing which I didn't show you is the stochastic model. So the stochastic model is, so to say, bottom up. It's purely based on particles and particle modeling. And we deduce a master equation which describes the statistics on the mesoscale. We have not yet finished the step to macro scale to the continuum level. So this is bottom up. Deterministic particle modeling. We develop a stochastic model on the mesoscale which describes the particle system. Okay, so that's option number one. If I don't get there, because I put it second, my numbering sucks. I put it second. Okay, if I don't get there, these are publications from 2015 to 2021 where this is described in detail. The option number two for continuation, and I hope I can finish that, that is the minimal continuum model that includes the stochastics, which I was referring to in the first part of my talk. So I would propose I continue with this unless you shout at me that I should do something else. I don't hear shouting, so I continue as prepared. So this, what I call minimal universal theory for gas, fluid, and solid, is different states, but it is not, be aware, it is not fluid-solid interaction. It is one material And it can be in a gas state, in a fluid state, and in a solid state. And the theory should catch all the transitions also, and all the transients, by the way, and the rate dependence, and many other things. Okay, so what I call minimal is I want to have as little state variables as necessary, as little as possible, but as much as necessary. Okay, and that are 4, in my opinion, and that can be discussed, but I think 4 is the minimum you need. Okay, so the first one is density, classical density, volume fraction. Density and volume fraction are for me synonyms. I will use one or the other. And then we have elastic strain. We could use the elastic stress, but I use elastic strain, and that was inspired by Mario Liu, who developed the GSH. And okay, but it's an inspiration. And if you talk strain or stress, then you have 2 possibilities. The first is isotropic, not sheared, not shape changing, but volume changing. And the second is deviatoric, shear, like shear. Shape change, no volume change. Okay, so you can split up strain or stress into isotropic and deviatoric parts, and that are the 2 state variables. In 2 dimensions, that's it. In 3 dimensions, you need a third one, but I skipped that one. Okay, and then number 4 is the temperature or the granular temperature. And if you really want to make your life complicated, then you have granular temperature and temperature, both. Okay, but this is not needed for powder systems and particle systems, so I stop with the granular temperature. The granular temperature is the kinetic energy, the fluctuation kinetic energy divided by mass. That gives us a velocity, and velocity divided by diameter gives us a time scale, a rate. So granular temperature in this definition is a rate, a 1 per time thing, and that one will show up in all rate-dependent phenomena. Okay, and universal, I call it universal because it contains all states and all transitions. At least all those which I could come up with. Maybe there are more. Good. Okay, now, GSH stands for Granular Solid Hydrodynamics. It was developed about 20 years ago and by Mario Liu, and plus means I added a few things to it. And since my expertise and what I do since more than 20 years is particle simulations, 1 plus stands for the particles, and the second plus for the particle model, and the second plus stands for the stochastic events, which are the PV and the PS, probability for isotropic and shear plastic events in an otherwise elastic system. Okay, and that's what I mentioned in the previous part of my talk already. Okay, and then you have density, elastic strains as state variables, and the granular temperature. Stress can be expressed as a function of the 4 state variables, so stress is not new, or you invert. Okay, density, elastic strain, granular temperature, I will continue with. Okay, and this is how the evolution equations look like. Time derivative of density is proportional to the isotropic strain rate and the density. Okay, that's mass conservation. This corresponds to the isotropic stress evolution. Here we write it as isotropic strain evolution, and it's proportional to the strain rate, isotropic strain rate, times 1, that's the elastic part, minus the possibility for plastic events. So the 1 stands for elastic, the PV stands for plastic. If you'd have no plastic events, you are purely elastic. If you have only plastic events, there is nothing remaining here. So 1 minus 1 would give you 0. Okay, and then you have relaxation dynamics. Tg is the relaxation rate, and it's proportional to itself. So this term, the time derivative, and this term gives you exponential relaxation, as I mentioned in the previous part of my talk. And this one is a mixed term. It connects the isotropic and the shear parts of the deformation. Okay, and then similar for the shear, time derivative, elastic, plastic, shear events. Relaxation term plus a mixed term, which I don't spell out here. Okay, these are 3. And if you do your deformations very slowly, that's good enough. The relaxation rate will be very small. Okay, but if you want to do faster, if you want to include rate dependence into the theory, then you need also an evolution equation for this relaxation rate. Okay, and that is the classical one. And then you have something which depends on strain rate itself, and you have something which depends on the yield. Referring to my previous speaker, how close are you to the yield of the material? And that also influences the so-called granular temperature, the relaxation rates. Good. Okay, so I start from the very, very basics, and that is the total energy density. So the total energy density has an elastic contribution and a thermal contribution, which corresponds to the classical thermal or to the granular thermal, and then it corresponds to kinetic energy. So we have two. The elastic energy we can deduce from particle simulations. DEM stands for discrete element method, and it is one method to simulate particle simulations, to simulate particles. And the elastic energy density is proportional to the density, to the volume fraction. There is the coordination number, there is an effective modulus, and there's the elastic strain squared. And there's the shear strain squared with the shear modulus in the second term. Okay, and since our granular matter have no long-range forces in the simplest case, the elastic strain has to be larger than 0, otherwise the elastic energy is not defined, so it's not there. So you have a transition from non-elastic. Above a certain density, at jamming, you will go to elastic, or you will activate the elastic energy. And maybe that's not all. There can be also thermal. Good. C stands for contact number or coordination number, or however you call it. And in the theory, it can be expressed as a nonlinear function with three coefficients, where alpha c is 0.5, delta is the elastic strain. So it's a relatively simple function which matches with the particle simulation data. So this is again the things which I added to the GSH theory because I know those things from my own particle simulations. So I intrinsically believe it. Okay, now if you take special cases, and that's what I hope to do.
So if you can conclude in 10 minutes time.
Yes, sure. Thank you for the warning. Okay, so if I want to understand a continuum theory, then I will take special cases. So the first special case is athermal. So I set Tg equal to 0, and that gives us a very simple subset of equations with which we can analyze. Or you can set the temperature to a constant that also drops out the evolution equation of temperature. But this is more related to thermal systems like glasses, as my previous speaker mentioned, or polymer melts, as I mentioned in one example before. Athermal refers more to granular materials because in many situations they are really athermal and the granular temperature can be ignored. Okay, and then you have everything in between those two, like transients and transitions. Now, there are some other cases. You can go to hyperelasticity if you set the probability for plastic events to 0. Okay, and then you can write down all the theory. It's a little bit messy equations, but it's straightforward to write down all the theory terms in the syntax which I was introducing. Okay, and then you also will get the tangent bulk moduli like compression modulus, shear modulus, and there's an anisotropy modulus also, which is due to the cross-coupling between isotropic and shear events, isotropic and shear strains. Good. So we have the total energy density, and the thermal kinetic energy, which I will not go into detail, is referring to kinetic theory. So everything here we know already from kinetic theory. It's classical thermodynamics, statistical thermodynamics, going back to Boltzmann. And in the last decades, it was extended to also add dissipation, which makes it relevant for granular matter. Okay, so from kinetic theory, we know some functions, analytical forms, which we can insert into the universal theory. Okay, and then here is the equation for the total stress, which has a shear and an isotropic contribution plus a dissipative contribution. Okay, so, and this is detailed in the paper from 21. Okay, I skipped this one. Now, if you have a continuum theory, you want to see whether it's thermodynamically consistent, so you calculate the energy and the entropy production terms due to granular and classical temperature We skip the classical temperature because it's really orders of magnitude smaller than the granular. Okay, so we focus on granular only. You can work with the Onsager matrix. We analyze all the terms which we have in the theory. I mean, the Onsager matrix looks ugly and complicated, but actually what comes out at the end are either quadratic terms or zero terms. And this one allows you to design a theory which is thermodynamically consistent. Entropy production is larger or equal to zero. It cannot be negative in this theory. Okay. Now, special cases. Why? That helps me understand things and also to calibrate, determine some of the parameters, some of the coefficients of the theory. Okay, so those of you who know granular material 40 years ago have talked about the classical granular homogeneous cooling state. So that's a special case. Take the granular temperature, it's decaying algebraically in a granular gas. In the gas or fluid state, the decay is algebraic, 1 over time for long times. In the elastic system, above jamming, it's exponential. So the theory makes a difference between the fluid state and the solid state. You see algebraic versus exponential decay. And this was something a surprise for me because the exponential I didn't know. I saw it in the theory first, and then I looked at my simulations again, and actually the simulations confirm what I observe, algebraic versus exponential in a fluid or in a solid. Hypoplasticity is a special case. If I want, I can go to a limit of hypoplasticity. I can do colloids at finite granular temperature, or I can do isotropic compression, which I will do in the next minute, or, no, not or, and I can define a large strain definition of the elastic strain. So you see, epsilon dot here is the total strain, delta or epsilon v is the elastic strain only. So that's a difference. You have total strain and elastic strain, and there's also a plastic strain, which I don't want to go into detail today. Okay, but anyway, this is the theory summarized in different words, the same as we had before. And if I go, short excursion, isotropic versus shear, I just want to highlight again, we can have a two-dimensional simplified strain tensor, isotropic, only diagonal elements. Isotropic means you are compressing from both sides, for example, in the same way. Or we can have shear, and that can be simple shear, like upper side goes to the right, lower side goes to the left, and that means compression and tension in these two directions. Or we can have pure shear, rotating this by 45 degrees, which means compression and extension in orthogonal directions also. So it's tilted by 45, rotated by 45 degrees. So we have isotropic and shear, just to make sure. If we go to the isotropic special case, a few terms in the theory drop out, and we can analyze the complete theory, all the state variables under some situations. I want to skip the details here, but I want to show you the strain rate before my time is up. This is pressure as a function of density, so related to some of the plots which I showed you before, and the different colors mean different rate. Okay, so the red line, which is actually hidden by the others below here, below the gray line, is the slowest. The magenta line, this one, is the fastest compression, and every x stands for one order of magnitude in compression rate. So the data set contains 5 orders of magnitude in compression rate. And that's what I meant when I said you have to go really, really slow to see the phenomenology which I was talking about. Okay, and you see, fast rate, very smooth. The slower you go, the sharper these plastic events get. And then you can analyze them if you have them. With the magenta, with the fast simulation, you never can see the plastic events. Pressure in logarithmic scale as a function of density. And very low pressure means we have no elastic contribution. And here the elastic contribution starts to kick in. And at very high density, there's no rate dependence anymore. because the rate effects are negligible as compared to the elastic effects. Scaling it gives us pressure, which is almost linear as a function of density or as a function of strain. I don't show the strain here. Okay, but there are these wiggles. There are these hiccups, these plastic events. A straight line would correspond to elastic, but everything which is not on a straight line is plastic. Okay, and this is the bulk modulus which we deduce, and the negative drops are the plastic events. For different rates, we do observe the same bulk modulus, and we get different information during the plastic events where the bulk modulus plastic event is not elastic, so the bulk modulus is not defined here. Good. So then you can play the game with the theory and with the simulations. I only show you the theory here. You can compress a bit, and then you can do small amplitude cyclic loading, ratcheting, for example. This is something, and you can measure the different densities which are involved in the system and their evolution. So the theory is complete in that sense. I can apply every boundary condition I want, and the solver will give me the data. Okay, so pressure, coordination number are results from the theory that are the lines, and then I can compare them to DEM simulation. I showed this one already, and we did the quasi-static TG equals 0. We did the comparison already in 2016, but at that time we didn't have a theory which contains the transients and the non-elastic states and the rate dependence. You can go further. I don't want to go into details here, but this is logarithmic long-term aging. I only give you the keyword. I don't tell you the details. This is the proof or the confirmation that the jamming density or the solidification density is a function of history. For different history, you get different densities in this gray area. So the consolidation density, the jamming density, however you call it, I do not call it yield density. The jamming density is a function of history. The yield density is another story. That's not the same thing. Okay, and you can do models with different friction coefficients, for example, just to mimic different types of real materials. And they also scale in the same way as the previous data, which were actually frictionless. Okay, and something interesting things are going on when you zoom in here. Dynamics is much more important close to jamming than for higher densities. Okay, and then you can do shear. I showed you the shear results already, so I don't want to repeat those, but I want to show you an animation of a shear event. Shear here is pure shear, so we have compression vertically and extension in one horizontal direction. The color means how many numbers, how many contacts has a particle. So blue is 0 and yellow and red are high numbers. So it starts again from the beginning. At a certain point, we get fragile, so a lot of bluish particles, and then it jams here. Elastic. Elastoplastic, I should say. Okay. Now, this is the end of this part of the talk. Unfortunately, I didn't get to the stochastic model. I was not fast enough to tell you everything I could tell you, but I want to stop here then. This is a didactical thing. I want to stop here with, give me a second, with the conclusion. Where is it? I showed you the minimal universal theory, particles continuum for all states, gas, fluid, solid. I showed you a few examples and the probability for plastic and elastic events. That one includes the mesostochastic events into the macro theory. So that's what I showed you now. Oops. That what I showed you now is a macroscopic theory where I phenomenologically include stochastics, mesoscale, based on particle simulations. So that was the top down. And if I would have another 20 minutes or 10 minutes, I could tell you something about the bottom up approach, where we built a stochastic theory. We have built a stochastic theory based on particle simulations. That one I'm still working on because here the connection to the macroscopic scale is missing yet. So what I showed you here is we have the microscale, the mesoscale, and the macroscale combined together in a macroscopic theory with all these features. Thank you.
Thank Stefan for the wonderful talk. So, any question? You can have question from the both the parts. Well, if not, then let's thank Stefan once again for the wonderful talk.